Hello, good evening, everyone. Buonasera a tutti. Tonight we will be having our first English live stream, and I'm very, very happy about tonight because we are having a very, very high-level guest. It's really my pleasure and honor to welcome Professor Gerry Thomas here. A quick presentation of our guest for whoever does not know her. Gerry has been chair of the Department of Molecular Pathology at the Imperial College in London, and she also is the director of the Chernobyl Tissue Bank, which is an organization that is studying the aftermath of the Chernobyl disaster for the past, I believe, 23 or 24 years.
Yeah, hang on, I have to remember now. We started in 98.
Yeah, so it's 24 years roughly.
24 years, yeah.
So definitely one of the most knowledgeable people in the world when it comes to the health effects of radiation and the consequences of the Chernobyl accident. So welcome, Gerry, and thank you for joining us.
Thanks, it's a pleasure. And I apologize that I don't speak Italian.
Oh, it's actually fine. I believe it's important for the Italian public too to get used to English speakers, because I would like to invite more international guests in the future. So I'm gonna start with a question that is a little bit personal. So according to your Wikipedia page, which I know is not the most trustable source, but I'm curious about this because your Wikipedia page reports that you used to be anti-nuclear. So when you approached studying the Chernobyl accident, you were not coming from a pro-nuclear stance, but rather an anti-nuclear one, and you changed your mind studying Chernobyl, which is unexpected, let's say. Most people have it like the other way around. Can you...
That's quite right, yeah. I mean, I think the way I used to see the world before was very much, I'm left-wing, as most academics are. We don't like the bomb. And I sort of came to it, I think, from that angle, and made the assumption that I think an awful lot of people make, is that nuclear power is like nuclear bombs. And of course, when you start understanding about nuclear power and how you modify the engineering so that you don't destroy everything in its blast, you are trying to get energy released over a long period of time using the same physics, but the engineering is very different around it. So the last thing you want is something that blows up like a bomb, and that didn't happen with Chernobyl, and it's never been designed to happen with Chernobyl. So I think I was expecting to see an awful lot more cancer incidents after Chernobyl. And you have to remember, putting this in some context, we tend to forget how long ago the Second World War is to most people. But to somebody of my generation, I was born in the 60s. I was brought up with all the anti-nuclear propaganda that we had, so that we did not want nuclear weapons because of what had happened in the 1940s in Japan. But actually, the studies of the cohort of people who were exposed only started in the early 1950s in Japan. So we didn't actually have that many decades of data that told us what radiation did, even in the event of an atomic explosion, a bomb explosion. So when Chernobyl happened, it was in the 1980s. And really and truly, we were only starting to understand the increase in cancer that we thought we might have seen after the bombs in Hiroshima and Nagasaki wasn't as big as we had expected it to be. And we were starting to realize that maybe radiation wasn't as bad as we thought, but we really didn't have the data as scientists to be certain about what we were looking at. And of course, now, with another 20, 25, 30 years of experience, we now can look at all of that data and really understand that radiation is not a really good carcinogen. It doesn't cause that many cancers, but we didn't understand that, I don't think, at the time Chernobyl happened. So everybody expected there to be lots of cancers, which there weren't.
Well, which also means that some of the remediation measures that were taken after the disaster probably were too much, but because back then we didn't know, it was justifiable to take those measures. Would you say so?
Yeah, I mean, it was very sad, actually. We had just finished a review of all the data we'd had after Chernobyl in 2011. We'd just written a special edition of a journal, and as part of the editorial, we'd actually said, look, we now know what happened after the Chernobyl accident. There was an increase in thyroid cancer. There hasn't been an increase in other cancers, and this is because the doses were so low. But the one thing we have not learned is how to communicate the real risks of exposure to radiation. And we just literally finished it, taken it to press, and then Fukushima happened. So we watched everything that we'd said, we have not learned this, just explode when it came to Fukushima. All the headlines, all the sort of overhype of the dangers of the radiation. We made exactly the same mistakes over again and evacuated people who probably did not need to be evacuated in the circumstances. But, you know, it's great having hindsight. But we're not actually reading our histories either.
Well, in Italy, we experienced this in a particularly dramatic fashion because our headlines were amongst the worst in the world.
Yeah.
If you consult the website jpquake.info, which gathers all the bad press that happened after the Fukushima disaster, Italian newspapers are topping all the charts of bad journalism, including several that still in these years are attributing the casualties to the nuclear accident rather than the earthquake.
Yeah, that is really, really bad. I mean, I was actually on the BBC television program of a live broadcast, and we had just seen the most horrendous sights of, you know, the tsunami and the earthquake. And then somebody had come on to explain that his wife had put his two children over the concrete wall into his parents' house, and then he'd never seen her again. And you think that's a total and utter tragedy. We find it really difficult to imagine that sort of thing happening because we're not exposed to things like tsunamis and earthquakes. And then they said, and now we come to the disaster, which is Fukushima. And I'm afraid I lost it on television and said, you should not describe this as a disaster. You have just seen the disaster. Do not forget that nearly 20,000 people lost their lives in the tsunami. Nobody has died from Fukushima, and still nobody has died from Fukushima. But you wouldn't have believed that from the headlines.
Yeah, absolutely. So going back to Chernobyl, you just said that the final report from your group of study came out in 2011. The initial reports that was submitted to the Chernobyl Forum in 2003 states that the total number of cancer deaths attributable to the disaster could reach 4,000. It also states that further studies will probably lack the statistical power to confirm or deny this number.
Can I just correct you on that? Because sure. you're quoting the Chernobyl Forum report. Now, the Chernobyl Forum report, and it's something that I see misquoted, did not say 4,000 cancer deaths. It said 4,000 cases of cancer. And there is a very important distinction between those two things. You can have cancer and survive it and die of something else. So yes. People say it's 4,000 deaths, but that's not what was said in the report, actually. It says 4,000 cases.
Okay. And anyway, do you think this number is a good estimate?
Well, I think it may be an overestimate in actual fact. And the reason that I think that is if you look at the cohort studies, that 4,000 number came from looking at the number of people who are exposed as what we call liquidators. These were the people who cleaned up after the accident. Now, some of them had quite high doses, but many of them came in many, many years after the accident and had much, much lower doses. So you've got a huge range of doses in that cohort. And since effect is linked to dose, obviously the lower the dose, the lower the effect. So you have to be aware there may have been a lot of people exposed, but not a lot of people exposed to high doses. But if you looked at that report, it had said, okay, we have this number of people, we have an average dose of this, therefore, using the LNT model, which we'll probably talk about later, we would predict there might be this number of cancer cases. And they took those figures from what we knew about exposure from the atomic bombs. Okay. Now, those cohorts are still being followed up today, and we have yet to see a single cancer case that is due to the radiation in that group. In other words, there is no excess number of cancers in the exposed groups compared with control groups. So that 4,000 may be an overestimate.
Okay.
But we won't know I mean, the problem is we won't know for several decades, because cancer can take 50, 60 years before you have a cancer that's been caused by something. So you have to allow that time to elapse before you can really say for certain.
Okay, so what about the other reports on Chernobyl? Because the Chernobyl Forum was criticized for being too soft on predicting possible consequences. The European Greens made their own reports, which is called The Torch. That's the other report on Chernobyl, which conflate the number up to, I believe, 20,000, and Greenpeace even made a report saying that the minimum number will be 93 or 94,000, but it could go up to all the way up to 6 million worldwide.
This is where you have to be really careful and understand how health statistics are derived. What happens over a period of time, and we are talking about, a number of decades now, is that the way we diagnose cancer changes. So cancer incidence can rise in a population, not due to radiation, but can also arise due to lifestyle changes, due to the fact that, one good thing is, we're all putting on more weight, and we know that gives you more cancers. So it can change to lifestyle cases, lifestyle conditions. It can also change the way you diagnose cancer over time. So the only way you can really be certain what the incidence is and when it's due to radiation is to do properly conducted epidemiological studies. You can't just pick numbers out of the atmosphere. It has to be a study where you take into account all what we call confounders in these studies. So changes in lifestyle, changes in drinking patterns, huge importance, changes in smoking patterns, changes in diagnostic patterns, changing in the way cancers are reported to the registry over time. All of those factors can affect the actual number of cancer cases that appear in the statistics. And the only way you can attribute to a cause is to look for an effect of dose. So where the dose is higher, you expect to see more cases. Where the dose is lower, you see fewer cases. And do those studies in what they call an epidemiological cohort study or case control study.
Okay, well,
Torch and Greenpeace studies don't do that, but the UNSCEAR report does take into account all of those.
Well, I know for a fact that after the dissolution of the Soviet Union, Ukraine experienced a big economical crisis, which led to an increase in alcohol abuse, and as well as the healthcare system was in pieces because there was like economical crisis, and well, that can definitely affect cancer statistics, I believe.
Yes, it can. Yeah, I mean, if you look at the WHO statistics, the biggest predictor for poor health, including cancer, is poor socioeconomic status. So if you have an economic crash, it really does have a serious effect on people's health, mental health and physical health.
So let's go to the specifics. Radiation can cause cancer. It's not a major cause of cancer, but it can cause cancer. How exactly does radiation cause cancer? So what's exactly the mechanism? Because radiation there are particles that carry on some energy, like alpha particles have a low penetration power, but they carry a lot of energy because they're massive. And beta particles, they can penetrate slightly better. They carry less energy because they are way less massive. And then you have, of course, gamma rays, and then you have neutrons as well. So what's exactly the mechanism with which radiation interfere with cellular reproduction?
I think the best way to do it is through the three sciences. First of all, you have physics. And so it does depend on whether you've got alpha, beta, or gamma radiation. Gamma is a wave, and it passes through your body out the other side without interacting with anything in your body. But it will also interact with the DNA within your body. Then you have beta, and the isotopes that produce beta radiation don't just produce one type of beta radiation. they produce lots of different beta radiations, have different energies. And the energy of those beta radiations determines how far and how strongly the radiation will interact with your cells. Alpha is, again, a different matter. Alpha won't go through your skin, for example. But if you take alpha inside you, then the alpha particles can interact with the DNA in your cells that are in your tissues inside. But for alpha and beta, you really need to ingest or inhale isotopes that are producing alpha and beta. For gamma, you can be exposed by isotopes that are outside your body. So there's those three sort of physical things. So as well on the physical side, you've got physical half-life, okay? And physical half-life varies with different isotopes. Then you have chemistry that comes into play. So does the isotope that you're taking into your body concentrate in any particular tissue? If it does, it's going to give that particular tissue more dose than it will give other tissues in your bodies, okay? Then you have biology. So if you expose children, they will show a greater effect of the radiation than adults. And that's simply because their tissues are still growing. So in the case of thyroid, for example, we know that the thyroid takes up iodine. So if there's radioactive iodine around, it will also take up radioactive iodine. Not only does it take it up, it actually binds it within the tissue, which means because it has a short physical half-life of 8 days, and it stays in the body for 100 days, there's a good chance it will emit its irradiation. And because it's concentrated in the thyroid, the highest doses are going to be towards the thyroid. Also, added to that, children have thyroids that are still growing. When you get to about 20, your thyroid stops growing. It reaches its adult size and it stays that way. It does not continue to grow. But in the child, obviously, it has to grow from a child's side to an adult side. So the thyroid is still growing. Now, that exacerbates any effect of the radiation on the thyroid cells. And basically, the way that radiation interacts is it is one of two things. It either hits the DNA and makes the cell misread the DNA, making like a typo error when you're typing quickly on your computer. You'll quite often make a typo error. That happens, and then the DNA is misread, which changes the sequence, which can lead to what we call mutations, so that you get a different base, and then the sequence is read differently, and you get a protein that is not regulated in the same way. It can also, if the radiation is of a strong enough energy, it's got enough heat energy, it can actually break both strands of the DNA. So it can cut across the DNA, and the DNA misanneals, and that's when you get what you call a translocation, when you get two different bits of two different genes that suddenly stuck together and make a completely novel protein. So those are the two biological mechanisms that it produces radiation by. But the effects of the radiation are really depending on its energy, depending on its physical half-life, depending on its biological half-life, and then depending on whether the tissue is growing and whether the particular tissue concentrates the radiation, which will give you a bigger dose. So something that has a long physical half-life, but a short biological half-life, actually does very little damage because you don't get very much dose, because most of the time that the isotope is in your body, it's not emitting radiation because it's got this long physical half-life. So it's really important. People get really worked up about things like uranium because they have very, very long half-lives. But actually, the dose that you would get from uranium is tiny. And actually, the chemical toxicity, because these are chemicals after all, they're not just physical entities, they are chemicals. The chemical toxicity with uranium is more of a worry than its radiobiological toxicity. Iodine is very different. Iodine is an isotope that has a short physical half-life and a longer biological half-life, so it will give a higher dose to the tissues in your body. And the dose really does make a difference. The higher the dose, the more likely you are to have a cancer form than if you're exposed to a much lower dose. Does that make any sense?
Which is, I believe, the reason why of all the isotopes that are produced in nuclear fissions, the most the ones that are considered more dangerous are the one that come out in gaseous form.
Yeah, it's partly the fact that you've got, well, it's really only radioiodine that's when you're looking at an accident like Chernobyl. We have no effect at all from cesium, which is also a volatile isotope, but that's because the physical half-life of cesium is very much longer than its biological half-life. So you get a very low dose to the tissues, and it doesn't concentrate anywhere in the body. So it just goes everywhere in your body. So actually, of the 6 million residents who lived in the area, who were not evacuated, but lived in the area around Chernobyl, over 25 years, they got a dose from cesium of about 10 millisieverts. And to give you some context, that's about the same as you get in a whole body scan in a matter of seconds. So that's why we don't see any cancers from cesium, because the doses were so much lower. For thyroid, the doses, particularly in children, were much, much higher. They were of the order of sieverts, or I think one case was even 60 sieverts was the highest that we actually saw, which was huge to the thyroid.
To a single organ.
To a single organ, yeah. Whereas cesium, it's just nothing. It's, it's less than one CT scan in 25 years, which is why we only see effects of radioiodine, and only in children who were children at the time of the accident. We don't see it in adults because your thyroid doesn't grow, so you don't have the same effect.
And what about strontium?
Strontium, again, is quite a heavy metal, so it is not actually dispersed in the atmosphere. It's interesting. There is data that's still available on the internet of when we were monitoring the weapons testing in the United States. We were watching what was coming over to Britain and measuring strontium and cesium in milk. We found strontium and cesium in milk in the 1960s from those tests. We only found cesium from Chernobyl. We did not find strontium, and that's because strontium is so much heavier. It just didn't get anywhere. It stays, where it's produced. It is not forced into the upper atmosphere from
it's not volatile.
An accident, as opposed to a nuclear bomb where it is detonated in the atmosphere.
Okay, and but in case there is an intake of strontium, is it concentrated? Because I've read
bones. Yes,
in the bones.
But again, you have to have quite high doses to produce osteosarcomas and things like that, and that you just did not see the amount of strontium released that would give those sort of doses. Okay,
and are there any other dangerous radioisotopes?
Not from Chernobyl. Those were the only two that, as far as the population was concerned, we can talk about the emergency workers later on if you want to, but as far as the population is concerned, it's only the volatile isotopes, and the two volatile isotopes of concern are cesium and radioiodine, iodine-131 predominantly.
Okay, I'm just gonna add a quick question. I already know the answer, but I believe that the public might be interested. What about tritium?
Tritium? Oh, don't make me laugh. Tritium is like having your DNA wafted by a feather. Tritium is really, there wasn't an awful lot of tritium released, full stop. But tritium, quite frankly, is the least of your worries. You'd have to drink 2 liters of tritium at the highest possible level that the WHO would allow you to drink drinking water. 2 liters every day for a year to get a fraction of the dose that you get from natural background radon every year of your life.
Yeah,
people have got this idea that tritium is really dangerous. Tritium is not. Its half-life is 12 years, and its biological half-life is 10 to 40 days. When you see a big difference like that, it's not going to give a big dose to the body, so don't worry about it.
Yeah. Also, there is something about tritium that the decay energy is very low. It's so low.
5.7 kilo electron volts. It's minuscule.
It's so low that it's on the edge of ionizing radiation. If it was like a little lower, it doesn't even have half of the time. Tritium beta decay does not ionize because the energy is dispersed as Bremsstrahlung radiation.
Yeah. Yeah, that's why I say it's like wafting your DNA with a feather. It's not going to do any harm.
Yeah, I know. I'm asking the question, of course, because I want to put this live on YouTube with subtitles and point this conversation to all the people who will ever complain about the Fukushima water.
Yeah, there's nothing to worry about. I've been to Fukushima 5 times, and I've been around the plant, and I've seen those huge containers where they keep the water. The water, actually, by the time they were releasing it, is lower than the regulated level that we could be drinking the tritium in Europe. And they were worrying about putting it into the Pacific Ocean, which would have a massive dilution effect as well. I mean, it was just crazy. But that's what I mean about risk communication and radiation. We've got it so badly wrong. People are frightened of the wrong things.
Yeah, and well, that's what the next questions tap into, because one of the reasons why people are so afraid of radiation is because the current damage prediction model, I would say, the LNT model, states basically that there is no safe dose of radiation. That even a single radionuclide can cause you a cancer within.
That's not true. Once you get down to the really low levels, below about 100 millisieverts, if there's a good thing that if people want to go and look it up, just type in Oxford Martin radiation restatement, and you'll get this document that comes up. And there's a graph in there that is really, really good, where they've taken all of the big studies that we've done of people who've been exposed to radiation for various things. So people like the lifespan study from the atomic bombs in Japan, some of the other radiation accidents, all the cohort studies we've got of workers who've worked in the nuclear industry, etc. And they put it all together on one graph. And if you look down below about 100 millisieverts, you start to see that the points are above and below the x-axis. So this is the risk prediction. This is what they call the excess relative risk that they've obtained from all of these studies. If you then add in 95% confidence intervals, and it is really important when you're doing biological studies that you do have those 95% confidence intervals, because we are such a varied species that we have to take into account that there is huge variation in different groups of people. But most of those confidence intervals straddle the x-axis. Now, if I was to show you that graph in any other circumstances and try and tell you there was an effect there, you'd laugh at me. If I was trying to present a drug and say, this is really effective at these low doses, you go, no, you're lying to me. That's just not what that graph shows. But for some reason with radiation, we look at that and go, oh yeah, well, there might be an effect. But the answer is you can't tell whether it's a negative or it's a positive effect of radiation. And you'll never be able to do the certain of that answer. You'd have to expose billions of people to very low doses of radiation, follow them throughout their lifetime, record every diagnostic bit of radiation they had in their life, every cancer treatment, radiology scan, whether they flew in an aircraft or everything. You'd have to do a huge study like that to be able to quantify those risks. Nobody is ever going to fund that. And it would probably still come out as, well, we still don't really know the answer. Because the risks that you have...
Professor, I think I cannot... I think our connection went down. Penso che le sia caduta la connessione. Vediamo se si riconnette. Intanto ho trovato l'Oxford Martin Restatement, quindi il grafico di cui stava parlando la professoressa Thomas.
L'ho già inviato in chat, amore.
Sorry,
Hello again.
I don't know what happened there. Everything just disappeared.
Yeah, I think your connection crashed. I'm showing the Oxford Martinez statement. I just Googled it and the screen share. And I believe that this is the graph you were talking about.
That's the graph I was talking about. So if you look at that, the lower dose, and that's actually below 500 millisieverts. But if you focus on the 100 millisieverts, so from 0.1 on the x-axis, it's extremely difficult to see whether there is actually any effect at all, because those studies straddle the x-axis. So, you know, how we ever sort that, I don't know. I don't think we ever will sort that. But to put that into some form of context, the sort of scenario I give everybody is, if you take 100 Americans, and we use Americans because we've got huge amounts of health data for all, you know, other causes of cancer, etc., and you expose each of those 100 Americans to 100 millisieverts, okay, only one of the people there is likely to develop a radiation-caused cancer. 42 of them will develop cancer for other causes. So as you drop that dose down, because it's a linear relationship, it gets even harder to see at the very low doses the one case at 10 millisieverts in 1,000 Americans, compared with the other 420 cases of cancers caused by other things. It just becomes impossible to sort the wheat from the chaff. And actually, as somebody who's interested in cancer, I'm more worried about what's causing the other cancers. The one cancer caused by radiation is not a great worry to me. The 42 others at 100 millisieverts is a great cause for me, and that's much more of a public health worry. So we tend to think that radiation is really dangerous at those low levels, but actually, what we eat, you know, what we drink, whether we take exercise, is probably having more effect on our health than being exposed to radiation, even at 100 millisieverts. And as I said, from Chernobyl, most people from cesium got 10 millisieverts over 20 years.
Yeah, and actually, I saw statistics of leading causes of death in the world, and the first one, of course, is high blood pressure. The second one is smoking, but an interesting thing is that among the top 20, there is secondhand smoking, which kills 1.2 million people per year worldwide. Radiation is like not even making the chart. And actually, I also know of a study which was completed last year, which was basically a survey of the whole United States population. The cancer incidence compared to background radiation, and I believe that there was not a strong indication, but a weak indication that actually the areas with with higher background radiation has lower cancer incidence, and that could be explained with the model which is called radiation hormesis. Which can you explain us?
Yeah, the radiation hormesis model is basically a little bit of radiation is good for you. So that if you're exposed to a little bit of radiation, it peps up your DNA repair so that you're actually better at dealing with all the other nasty things that can give us cancer around. I think you have to be really careful. I think we'll ever prove whether it's an upward curve or a concave or a convex curve at those lower doses, because we'll just never be able to do the studies properly to tell us that, because it's such a small effect. I think, you know, the other thing you have to be very careful about is where people tend to have higher background radiations, that they also tend to live in slightly elevated areas. So up in the mountains, for example, in Colorado. So those people tend to be fitter because they tend to enjoy their winter sports, and they'll tend to drink and smoke slightly less than people living in urban environments. So you have to be really careful that the environment people live in can have a major effect on their health. In fact, if you live in London rather than somewhere like Inverness in the north of Scotland, which is lovely, but there just aren't any jobs there. But if you live in London, you have a significant effect on your mortality by living in a congested city with lots of air pollution. And that's another thing that people forget is, you know, air pollution causes many more people than anything to do with radiation ever has done, including the bombs.
Yeah, and air pollution is actually the fourth leading cause of death worldwide, killing several million people a year. And so what do you believe would be the best model for predicting cancer incidence after exposure to ionizing radiation? Do you think we should?
I think we should stop trying to predict it. I think it's such an unreliable prediction that you shouldn't use any of the curves that you might want to use down at that end, because other factors are so much more important. You're looking for the needle in the haystack, and actually worrying about that needle in the haystack is probably doing an awful lot more harm than just saying, okay, well, if it's lower than my total radiation dose. So for example, say in the UK, we're exposed to 2.4 millisieverts per year of background radiation. So if you work out how much you're exposed to over 50 years, that's 100 and something. So you could sort of say, well, below about 100, which is doubling the amount of time that you're going to be exposed to background radiation for 50 years, then really, why are we trying to worry about it? Because actually the risks at that level are so much lower than other things that we can do something about, like, being fit and healthy, not drinking too much, not eating too much, etc., certainly not smoking. So why are we trying to quantify a risk that is so tiny when other risks are much, much greater in terms of public health in particular?
I'm just going to help your explanation with this figure. This is from the Joint Research Center report concerning nuclear energy, and this shows how do we get in touch with ionizing radiation. It's basically radon is playing the bigger part, and then you have soil, cosmic radiation, radiation from food, radiation from nuclear medicine, from artificial and medical radiation. And then you have this 0.0072% of radiation coming from nuclear technologies, of which the vast majority is weapons fallout, which is 0.005, and then the Chernobyl accident is 0.002, and nuclear electricity is 0.0002% of the total amount of radiation that you are exposed to. So it's like several orders of magnitude less than the natural radiation we encounter. And we also have actual evidence that there are areas in the world that have much, much higher background radiation. And did you happen to make studies on those as well?
I haven't made studies on them, but I know of the studies because it was part of that radiation misstatement that I was talking about that we put together after Fukushima. But there's always a slight caveat with those areas in that they don't have huge populations. And when you're looking for a rare effect, you need a huge human population to find it in. So the caveat that's always thrown at those studies is, well, the population isn't big enough. So unless it was a very big effect, you wouldn't see it. So you can't discount it's a very small effect. But a lot of people actually go to places where there's more radiation because they think it's healthy for them. And I've seen in spas in Japan, some of them actually say, we have put more radon in to make it healthier for you. And you're thinking, hang on, how does that work? But it's this popular misconception that anything that God has made for us is better than what man can make for us. Anything that man makes is dangerous. We see that with the pharmaceutical industry as well. Most of our drugs actually come from study of plants many, many years ago. We studied plants and we used plants in medicine. But as we got better at chemistry, we started extracting the active ingredients of those plants and we made a pharmaceutical industry. But people still mistrust the pharmaceutical industry because it's an industry and man is synthesizing things. Whereas actually some of the natural stuff that we used to take is really quite dangerous. You get the dosage wrong, you can really be quite ill with some of the plant-based medicines that we used to use many, many years ago. So it's interesting, there is this problem we have with human nature. If man makes it, it's bad. If nature makes it, it's fine. You can just have as much of it as you want. And yet it's all the same thing.
Yeah, actually, because the next question would be concerning Fukushima, I will start with another anecdote. in 2012, someone discovered that the radiation levels in Rome were much higher than Fukushima ones.
Yeah.
Because Rome is basically made on a kind of stone which we call porfido. I'm not sure of the English translations, which contains high levels of radon.
Yeah.
So there are certain neighborhoods of Rome which are very radioactive, particularly the St. Peter Square.
Yeah.
And someone discovered this and published on the internet, hey, Rome is more radioactive than Fukushima. But instead of tranquilizing the people in Fukushima, it actually scared the people in Rome, and they started protesting. So the mayor went on TV and declared, well, yes, Rome is radioactive, but radioactivity here is natural, so we are fine.
Yes. I got into a lot of trouble when I was talking to the media about Fukushima, because I pointed out that there are areas of our country that are more radioactive than the areas around Fukushima, and one of those is Cornwall. Now, the Cornish Tourist Board didn't like me very much because they thought, I was stopping. I mean, Cornwall's beautiful, but it's full of granite, and if it's full of granite, it's going to produce more radon. So the natural background radiation is going to be that much higher. And unfortunately, some of the nicest places in the world are the ones where the radioactivity is higher. But it is natural, so it'll be fine for you. That is just the physics just doesn't work there. Radon is the same as radon produced by man as produced by the earth. But unfortunately, we do have this idea that if it's natural, it's fine.
Yeah, there was also an article on a major Italian newspaper a few years ago advertising Guarapari. The Guarapari beaches in Brazil has a very as a wellness location for your summer vacation.
In the sand.
Yeah, and it is mentioned that natural radioactivity helps your body, and it's like it's monazite. It contains thorium. You can craft nuclear fuel out of it.
Yeah, exactly. It's nice and warm because it's radioactive, and actually, warming your joints is very good for arthritis. But you can do it in other ways than sitting in thorium sands.
Yeah. So because we spoke about Fukushima, you mentioned having been there. Now, the radioactive release in Fukushima was way less than the Chernobyl one, but it still affected people, apparently. I mean, there were a lot of evacuees. Can we expect...
They were very cautious. The Japanese... There are sort of limits set by ICRP, the International Committee for Radiation Protection, that sort of suggest levels at which you might want to evacuate people. And they give a range between 20 and 100 millisieverts and a dose in a year. And unfortunately, the Japanese went for the 20 millisieverts. So they evacuated an awful lot of people. To be fair to the Japanese, you have to bear in mind there was an earthquake and a tsunami. And so there was an awful lot of infrastructural damage. So rather than risk people going in and out of the radioactive areas, they probably thought it was actually safer to evacuate them because it meant that no emergency workers had to go in and work, for example. But actually, there really wasn't a need to evacuate from the radiological perspective those people. But there might have been other reasons they needed to evacuate them because of the infrastructural damage.
And can we expect any sizable, measurable increase of cancer rates in those exposed to...
Absolutely none. That you'll see reports in the media where they say that the Japanese government has paid compensation to, I think it's 4 people who developed cancers of various types after Fukushima, who were part of the workforce. But be very careful. There is a Japanese statute that agrees a certain level at which compensation is paid. It doesn't mean that actually there's any scientific meaning to the fact that they were exposed to radiation, because all the scientists look at the doses that people were exposed to and go, we can't possibly say that is a radiation-induced cancer at those levels. But unfortunately, there is a Japanese compensatory mechanism. So there's a difference between attribution and compensation. Attribution is when you attribute an effect to an exposure. Compensation is when you pay up legally because it's cheaper to do so rather than go through the court.
Okay.
Those reports. There is no scientific evidence, and there never will be, because we know what the doses were from Fukushima, for anybody to have a radiation-induced cancer following Fukushima.
Okay, and what about newborns? Can radiation affect upcoming future generations, because in Italy, I don't know if in the rest of the world it was the case, but in Italy there is this legend that in the Chernobyl exclusion, in the Chernobyl area, the area affected by the Chernobyl fallout, there are still babies being born with malformations and so effects.
Totally untrue. Unfortunately, there's actually a very high level of congenital abnormalities. I can't remember the exact figure now, but there's quite a high level of natural congenital abnormalities. And unfortunately, when you have something that you can blame, you tend to blame that for it, even though it's a perfectly natural occurrence. There is no evidence at all for congenital abnormalities. There's no even evidence after the atomic bombs, apart from the very few numbers of women who were exposed when pregnant to very, very high doses, and I'm talking, sievert level of doses, to gamma radiation. A few of those gave birth to babies who had neural tube defects because they were exposed at the right time in pregnancy. There is this total misunderstanding of radiation in pregnancy. Radiation can only affect a fetus at a certain time point, and what you tend to see is neural tube type defects that affect the brain function. After the atomic bombs, with the lower dose cohorts, there was no effect seen at all. But very, very sadly, and I've met people in Japan who've told me they've not had children later in life because they were exposed to the atomic bombs. So they've taken an active choice not to have children because they believe there might be an issue. The latest research we have on this is there was a whole series of Chernobyl liquidators, so people involved in the cleanup who had much higher doses, therefore, than the general population, who had blood samples taken. So men and women, mainly men, but men and women who'd been working in Chernobyl, who then subsequently went on to have a child. And they did whole genome sequencing on the blood samples from the mother, the father, and the child. There's absolutely no evidence of any effect of the radiation on the child's DNA at all. So that's idea that exposure to low doses of radiation is going to cause problems in the next generation is just totally wrong. And that really should be the study that nails that myth.
Yeah, well, because it was in the original LNT, the original LNT author, Muller, proposed this idea.
From fruit flies. I'm not a fruit fly.
Yeah.
I mean, that's another problem is that you have to remember that a lot of the early stuff was not done on humans, and humans, we know now that cell lines and different animals are not actually really good models for what happens in the human. We've known that in cancer for a long while, which is now why we tend to look at human tissue rather than use an awful lot of models, because the models do not really reflect the human when we talk about risks of exposure to chemicals or to radiation in terms of generating various things. So be very careful that you choose the right model before you start saying this is going to work in the human.
Well, I would also add that he used fruit flies, and he also exposed them to like the lowest dose was like 2.5 sieverts, which is fairly high.
Doses. Yeah, if you exposed me or you to 2.5 sieverts, we probably have acute radiation syndrome. So those again, the old studies don't really help the argument going forward, because people always think that those are the doses you're exposed to from a radiological accident like Chernobyl or Fukushima, whereas the doses are in millisieverts and some of them microsieverts. So thousands of fold lower than those early studies were using on an inappropriate model species as well.
Okay, I'm going to ask you final questions. That's a question that's probably a little bit harder because it's not strictly scientific, which is how can we better convey these messages? How can we better explain to people that radiation is a natural phenomenon, that it's happening inside us all the time, all around us all the time, and that below certain doses we should not absolutely be afraid of, because literally everything that we regularly deal with is more dangerous.
Yeah, I mean, I've just been reading something about them finding microplastics in blood samples in the Netherlands. Now, they're very careful to say in that report, just because we found them doesn't mean they're causing us any harm. We need to look a bit more about this, but with radiation, we go, oh, look, we found something, therefore it's really, really dangerous. And it's interesting the different attitude we take to things. And I think with radiation, you are exposed to radiation. You cannot avoid radiation. If you want to live on this planet, you have to be able to live with radiation. Now, that means our species has evolved knowing how to cope with radiation. We have mechanisms in our body called DNA repair mechanisms that monitor our cells every minute of our lives. And most of the time, they make sure that no nasty mutations come through to the next generation of cells. Occasionally, they slip up, and that's why there is a natural instance of cancer. Nothing to do with radiation. It's something that we have to monitor for every single time we divide. So, you have to realize that we have these mechanisms, that they exist to protect us, and therefore they've evolved along with us being exposed to radiation. So we shouldn't be worried about the very low doses that we're talking about. High dose radiation, yes, you should be. But if you think about what else we use radiation for, people tend to think radiation is all bad. If we didn't have radiation, we would not be curing cancer. And if I give you some idea of the dose that you would give a lady with breast cancer, the total dose would be something like 50 sieverts. Now, we don't give it all at once because we kill the patient. We fractionate it. We give it over lower doses over a protracted period of time. But without that radiation, a lot of people with cancer would die. So radiation can actually be highly beneficial for us, used in the right way at the right levels. And so we shouldn't just assume it's all bad. So I think we have to talk more about radiation. It's something that I think has stopped being taught in schools because people think it's dangerous. So you must. I mean, I remember having the alpha source with the perspex shield and the lead shield and a piece of paper, and you had your beta source,
which is completely useless with an alpha source. Like the dead cells of your skin can.
Yeah. But very vividly, I remember that experiment teaching me that alpha, beta, and gamma were different things. And so that the gamma would go through the perspex and it would go through the paper. The alpha wouldn't go through anything. And depending on your source, the beta might go through the paper, but it wouldn't go through the perspex. So it gives you a sort of a framework in which you can start to understand radiation. But I don't think that sort of thing is done in schools any longer because people regard it as too dangerous. And also get rid of the idea that a single atom that is radioactive will give you cancer. There's just no evidence for that. You have to have a certain amount of damage in your body in order for there to be a mistake made in a significant number of cells that you will then go on to get cancer. Biology is very, very complicated. Physics is easy, she says, who didn't do very well at A level. But physics is actually straightforward. Biology is incredibly complicated. And the biology that we have to deal with the physics is actually protects us to a huge degree. And I think you should read the reports that come out of UNSCEAR for Chernobyl and Fukushima and realize that the biggest health detriment has been people's fear of radiation, making them do inappropriate things, making them be fatalistic, not look after themselves, making them depressed, causing economic hardship, where people won't eat the produce from the areas that have been contaminated with radiation, ruining people's lives. That has much more of a health detriment to the population than actually being exposed to the radiation. Now, we can control that as a society. We can stop making people fear radiation and put a stop to all of that hardship if we choose to do it. And I think we, as a society, should be choosing to do that. We should be talking about radiation more. We should be explaining all of this to people, and where we can, demonstrating it in schools so that people grow up understanding this sort of thing.
Thank you very much. That's also the purpose of having you here as our guest tonight. I would like to thank you for answering all my questions, and I would like to ask the chat if they have some. And I'm already seeing one here. I think the answer is fairly straightforward given what we've said so far. but I think does it make sense? This is a typo. Does it make sense that after a radiological exam, like a scintigraphy, you have to stay far away from children?
It depends on the what you've been given in that exam. So, for example, if you were given a radioiodine, for example, to treat thyroid cancer or something like that, then you might excrete a certain amount of radioiodine. Now, it's not going to be a huge amount, but they will always be very, very cautious and say, well, don't hug your children because you've taken a radioactive isotope into your body. They are worried that they might come into contact with you. The actual chance of anything to happen to the child is minuscule, but because everybody always works on this precautionary principle, they will say, don't go anywhere near children. But, if you've gone in and you've had an X-ray or something like that, or, you've been treated for cancer using a cobalt source or something like that, where it's gamma radiation, you aren't asked to stay away from people afterwards. So again, you have to be aware of what type of radiation it is. If it's an isotopic form, the chances are the advice will be to stay away from children. But realistically, you're not going to give that child a dose that's going to cause any effect. But because it's precautionary, people will tell you to do it.
There is another question. I think I lost it, but it was sent to me privately, which is we should reflect on the expression "we have no evidence," which you use, of course, tonight several times. I also use it all the time because I come from a scientific background. But for a scientist, that means we have nothing to worry. There is no evidence that we have something happening. But I believe that to the public, that means we should worry, because having no evidence doesn't mean nothing is happening. And
and I think it's a scientific mindset. We rely on evidence. If there is no evidence, that means then there's nothing to worry about. You're dead right. It's difficult because I was brought up in a scientific household, so I don't understand the other viewpoint. For me, everything is about evidence. And I will always say to somebody, if you're going to make a statement, give me the evidence, and then I'll believe you. And I don't know how the general public would like us to express the fact that there's nothing to tell us that there's a problem, because that's what we're trying to say.
And someone is asking if you ever done any risk assessment study on nuclear waste.
Yeah, well, nuclear waste, again, is one of these big bugbears that people are really worried about. But actually, most of the nuclear waste that people tend to worry about is the long-lived isotope waste, which actually doesn't give a large dose to your body. And by the time the waste leaves wherever it is being stored, it's been packaged so well that nothing is going to come out of those containers at all. And in fact, the Swedes have done some modeling for their geological disposal facility, where they hypothesized that every single barrel they put down there leaked. And they still came up with a sum for exposure that meant you got a fraction of the dose. I think it was something like 3 hours, a dose that was equivalent to 3 hours in an aeroplane if you stood on top of the geological disposal with everything leaking for a whole year. So the answer is, from nuclear waste, there is so little dose. By the time they've packaged it all up, there's so little dose that you really don't need to be concerned about it. And people think we don't know how to deal with nuclear waste. Oh, yes, we do. It's the one thing we really do know how to deal with. And also remember, nuclear waste decreases in activity over time. Okay, long periods of time for some of the waste, but actually some of the chemical waste we produce, those chemicals don't go away. Like mercury, for example, persists in the environment for a very, very long time and does not decrease in activity or in hazard, whereas radiological waste does decrease with hazard. So I have not carried any experiments on nuclear waste, simply because it's not what I do, and there aren't any studies where people have actually been exposed to nuclear waste, apart from inappropriate disposition, like the Mayak workers in the Russian Federation. But they're all epidemiology studies. I haven't been involved in those.
And I believe also the Mayak repository was a military one.
It was, yes.
Because they have their own set of rules that military have.
Yes,
armies.
it's very different. Yeah.
And Oh, this is a maybe this is a probably more personal than scientific, but I think that's because you mentioned coming from a left, politically left background, which is the same as I come from. So why most green parties, which are genuinely striving to fight climate change, are also against nuclear energy? And I think this goes along with this one. What's the worst misconception about radiation that did the most damage?
Yeah, I think the fact that we're all scared of radiation and are saying no to nuclear is the thing that will actually do most damage to the human race, because I think nuclear is the only way that we are going to be able to mitigate climate change and have the sort of lifestyles that we want to be able to do this sort of thing. We need electricity to do this sort of thing. We can't do that if we, I mean, it'd be no good me trying to do it now. There's no wind outside and it's dark. So I would have no power to power my computer to be able to do this unless I was getting some form of energy from a different source. I think going back to the Green parties, it's been really interesting actually since Fukushima. I would never have approached a Green group to talk to. And I was talking to one of my son's friends' mothers from school, and she happened to mention she was part of the Green Party, and she wanted me to come and talk to the Green group that we have in the village here. And that was my first exposure to them, and I thought I was going to be fried. I really did. But they actually were very keen to know what the scientific evidence was. And after that, I started talking to an awful lot more Green groups. And some of our activists in this country, people like George Monbiot, who writes for The Guardian, which is a very left-wing newspaper, he was put in contact with me with one of the other professors in Imperial. And he sort of said, well, you know, why do you hold the views you hold? And this lady, Helen Caldecott in Australia, you know, is a pediatrician. And yes, you know who I mean. He's totally different. And I said, well, look, I will give you all my data. I will give you all the sources. I will back everything I say with a piece of evidence. Ask her to do the same. And he, after a while, wrote a really good piece in The Guardian. And I really admire an activist who changes their mind. And he just turned around and said, but the Green Party's been lying to us. Greenpeace has been lying to us for years, and we have to start looking at the evidence. Why do we want to look at the evidence for climate change and argue for that scientific evidence and use that, and we ignore the scientific evidence for nuclear energy? So, you know, I've talked more and more to Green Party, and in this country, we actually have the Greens for nuclear energy. They have a separate offshoot group. So I don't think the argument is completely lost. I think there will be some people who you will never ever persuade that nuclear is the way out of climate change. And that's just because they are people who are so entrenched in their beliefs. It doesn't matter what you showed them. It doesn't matter what science is out there. They just don't believe the scientists because they think we all work for the nuclear energy suppliers. Yeah, exactly. I mean, I've had people say, well, you've written for Unskier, therefore you're paid by industry. They really ought to come to a few Unskier meetings. I mean, we sit and argue over 2 or 3 words in a paragraph for 24 hours because we have to make sure that it's absolutely right. None of us work for the nuclear industry. We'd be a lot better dressed if we were. But, you know, it's just a group of scientists looking at the evidence saying, what's wrong with this paper? What's right with this paper? Has it been well written? Can we trust the results? So those are very, very, you know, I think authoritarian papers to read. There's a certain amount of political because all the countries like their voices heard. So you have to make sure that you've looked at papers that are written in French, for example, or Italian or what another language, to make sure you've included all of the papers from all of the nations that work together. But, you know, when it comes to it, if you look at the evidence, there is just no way out of this. If you want to have some form of climate change mitigation that enables us to keep our industrial societies going, keep the sort of lifestyles we've got and the benefits with healthcare as well that we've got because of those lifestyles, then you're going to have to use nuclear energy. It's no good going back to gas like Germany have done. You can see where that's got the Germans, you know, and you have to balance all your risks, and the risks from nuclear power are small and the risks from climate change are huge.
Speaking of risk perception, the risk of climate change are probably still not fully understood by the general public because they manifest slightly more over time. But yes, you know, it's like the usual car versus plane argument.
Yeah.
Like the effect of a plane crash are very immediate, and you lose 200 or 400 lives in a minute.
But every year we lose 2,000 on the roads.
Yeah, and like the safety rate of planes is ridiculously higher than any other mean of transportation, including walking.
And of course, you realize if you go on a plane, you are exposing yourself to more radiation. And that's another thing. People have said, well, don't you worry about radiation? I go, well, when I get on a BA flight and it says, do not come on here if you're pregnant because we will be flying at this amount of feet and you will be exposed to this amount of radiation, then I'll take it all seriously. But I've been on planes with people who took dosimeters who've then gone around Fukushima, and they were extremely disappointed that the rate on the flight was much, much higher than they did from walking around Fukushima.
Okay, there are a couple more questions, then I will let you go, and thank you once again. I think this is will be flattering for you, because someone's asking if you were the character inspiring the female character in the HBO Chernobyl series, like the woman.
I have to admit, I've never watched the HBO series. It's not good for my blood pressure to watch things like that. I watched the first episode. It wasn't on terrestrial television here. It was only on
digital
television. So I didn't subscribe to the channel it was on. But the first episode took me 3 hours to watch, because I kept having to stop it and go, that's complete rubbish, because there were so many scientific inaccuracies in it. And if you ever want to go and read all about that, if you look at a person called Robert Gale and Cancer Letters, if you put that into Google and HBO, Robert Gale was one of the people who actually treated the emergency workers at Chernobyl. He was a medic who was there treating it. He was brought in especially from the States. So he knows exactly what went on. He's an expert in hematology. He's still working now. Really, really fantastic guy. And he wrote a whole series of letters to a cancer journal, and to put it on social media would be much better. But he wrote a whole series of letters to a cancer journal telling them what was wrong with every single episode. So I would recommend that if you want to see what was wrong with that series, go and have a look at that. I don't think I can claim to be anyone who inspired that series, though.
I will definitely look at it. I made myself a commentary on the series from a physical and like reactor physics point of view, and the series is not totally inaccurate on that side. I mean, there are some exaggerations, but it's mostly accurate, and at very least, it portrays very well the chain of human mistakes that had to happen in order to cause that disaster, and yes, why it would. And also the leading character, Jared Harris is the actor portraying it, is very clear in the final episode when describing the chain of events that led to this disaster. Is very clear in explaining how that would never have happened in a Western reactor. Yeah, just absolutely. Because the higher level of uranium enrichment allows for more stable reactions, and you have a containment building and so on, and you have a negative void coefficient which cannot cause a feedback loop, and etc.
But the guy the producer who produced that, he's actually pro-nuclear. So he wanted it to come out as a pro-nuclear program, which I think, if you aren't blown away by the myths, and the fact that I can't remember the lady's name, but the fireman who died, and she then had
Vasily Ignatenko.
Yeah, his wife could never have got the dose that would cause any effects to her child and things like that. And I was so concerned I might have got that wrong. I actually contacted Robert Gale and said, look, you were there. Am I right in thinking this is completely wrong, or am I missing something? He said, no, you're right. There's absolutely no way that she could have got a dose that would have affected her child.
Yeah, also, there is this representation of radiation poisoning as something contagious, which doesn't make a lot of sense.
Wrong. But it's interesting how, even those of us who really know the science, when you see something portrayed as dramatic as that on the screen, you question yourself, because you think, am I missing something? Have I got this wrong? The best thing to do is to go and find somebody who actually, was there and knows it all.
And so there is one more question about the aftermath of Chernobyl, the event, not the series, which is sarcoma and leukemia case detected after the Chernobyl incident are average or greater?
No, the only cancer that has been increased in the population is thyroid cancer, and only in those who were children when they were exposed. So there's no effect on children now from the accident at all, because everybody is now 35 plus who was around at the time of the accident. So it's only thyroid cancer, and it's only in those who were children. And the good news about thyroid cancer is we can cure thyroid cancer. We have a 1% mortality of thyroid cancer. And that's because, ironically, we use very high doses of radioiodine, the same thing that caused the cancer, but very high doses to kill off any cells that remain in the body after we've taken the thyroid out. And that's an extremely effective and very targeted treatment, probably the best targeted treatment, if we're honest, that we've got for any cancer at all.
Okay. Oh, this question actually I was curious about. I forgot to put it in the list. After the Chernobyl disaster, several governments in Western countries adopted very restrictive measures, including in Italy. I wasn't born yet. I was born in '88, but I've been told. I was told by my parents that they were forbidden to drink milk, only powder milk, and certain vegetables were like were destroyed because they were in fear of the radioactive cloud, they called it. Were those measures excessive, or were they justified, or were they a little bit like maybe excessive, but I mean, better safe than sorry?
They were excessive, very excessive. I mean, we've had restrictions on eating sheep who were grazing on the hills in Wales that have only recently come off. And they've only recently been stopped because the farmers got very cross when the government tried to withdraw their compensation. But I mean, it's absolutely ridiculous. The amount of radiation we got was extremely small. The important bit of the radiation, the iodine 131, because it only has a half-life of 8 days. By the time the radioactive cloud got to the Western Europe, there was virtually no radioiodine left in it at all. So, you know, cesium doesn't make a difference. And actually, in this country, we had more cesium from, which is something we'd like to forget, but we had actually more cesium come across and get into the milk in this country from the atomic tests in the 1960s. And there's been no effect of that. So I mean, it is really, really mad the lengths we went to. And that's why I get really cross, having just, you know, had to deal with a whole load of media attention about things that were being said about, you know, well, what happens if the Russians have a problem in Chernobyl now and there'll be another radioactive cloud going across? No, there won't be another radioactive cloud going across Western Europe. And even if one of the nuclear power plants did have a fault that released radiation in some of the other reactors that are still active in Ukraine now, it would still not cause any significant issues at all in the West. But you can see why the Ukrainian government might want to talk that up to try and get the West interested in actually doing something to help Ukraine at the time.
Yeah, I know. We actually wrote several pieces on this issue during the last weeks because, of course, Italian newspapers once again proved their worth by spreading a lot of alarm about possible nuclear fallouts, to the point that we had my Facebook page we received several messages from drugstores asking to make a call to the population to stop buying iodine pills, because we had people.
It's the worst. I mean, you really should not take iodine unless you're told to by a doctor, simply because if you take too much iodine, you can actually block your thyroid and cause yourself an awful lot of problems called the Wolff-Chaikoff effect. So do not take iodine. And the only people who should be taking iodine are those who are going to get a significant dose of radioiodine and who are children or lactating mothers. And you would never be able to get a significant dose from any reactor that went bang in Ukraine now, by the time it got to Italy, there'd be so little radioiodine in there, it wouldn't be worth doing. And you could actually damage yourself far more by taking iodine. So please don't.
And because of we literally had a major Italian newspaper, and the major columnist of the newspaper opening the day after the fight in Zaporizhzhia, the biggest nuclear plant in Ukraine. He wrote, "This morning I woke up and discovered that Europe could not have existed anymore." And this is the level of misinformation. It's disgusting, but that's why our page is so popular, because newspapers aren't doing their job.
But don't worry, it's not just in Italy. We have some equally bad newspapers in the UK, but now they've actually learned after Fukushima, listen to the scientists more. And they complained. I mean, it was interesting working with the journalists, because they complained, well, we couldn't find anybody to talk to, because most scientists hide. They don't like journalists that much, but it's very easy to find a green activist to give you a slant on a story. So that's why we were hearing more and more of the green activists approach, which was scaremongering, and none of the science. And because we all came out of the closet in Fukushima, now a lot of the British press know they can come and talk to an academic who will explain things to them. They can go talk to anybody else if they want to, but at least they get the academic viewpoint as well. I would advise Italian scientists to get much more involved with their press.
I'm trying to do it myself, and I'm trying also to involve more Italian academics, because I come from an academic background, but I'm not an academic myself. But unfortunately, Italian newspapers seem to be interested only in selling the story that sells more copies, which is the scaremongering one.
But they will change. The British press did. They will change, but it takes a long while.
Okay, I'm gonna. This is the very last question. Then I will let you go. But it's interesting. Can you tell us if there's some evidence on health effect due to the wind scale accident?
Again, the doses that came out of wind scale were minuscule, and they actually had buffers fitted on the fire stacks, which actually took an awful lot of the isotopes out of the effluent that was coming out from the fire. But the doses were minuscule, much lower than Chernobyl, and I think they were even lower than 3 Mile Island, if I remember correctly. So they were tiny weeny doses, much less than you get on a transatlantic flight, for example. That's why we don't see anything.
Okay, well, thank you very much, Gerry. You have been extremely clear. You have brought us a lot of information. I believe our public is enthusiastic. I'm not sure if you're reading the comments.
I haven't got the comments up at the moment.
Okay, there is really a lot of enthusiasm. They're really thanking you. They're very, very happy of what they learned tonight. We had, by the way, 350 people watching us, plus, of course, everyone that will watch the video once it's uploaded on YouTube. So I would like to thank you again for having been our guest tonight. And if you will ever want to come back, our door is always open. And I will keep you posted once the video is out on YouTube with subtitles.
Thank you very much. And thanks everybody who's listening, but please don't have nightmares. Go away and have a good night's sleep.
And I'm gonna go offline.